code equivalent, as they're both certified by the PRG 320 standard. So as we go through the conversation today, you will hear Reid, Jack, or myself say mass timber, and when we talk about that today, it'll either mean the CLT or mass plywood, and that will be interchangeable. If we say CLT, you can also substitute mass plywood into that as an option. So when evaluating the panels you want to use on the project, you need to consider sourcing. CLT is widely available. You can see on the blue dots, it's many locations in North America and in Europe. And it's important to understand that mass plywood is a single source here in Oregon. Each manufacturer has different panels and different layups, and therefore it has different structural properties. So as we get into the design of these systems, we as engineers need to understand the differences between these manufacturers as we kind of work towards selecting the right product. Seismicity also plays an important role when looking to use mass timber as your lateral system. It obviously will impact the extent of walls you will need and the fiber quantity in that walls. It will also influence the code path that you have available to you as you kind of look to permit the building, it will also influence the conversations that you have with those jurisdictions. For example, low seismic regions may be more open to these new materials and these new lateral systems than a high seismic region. So you can definitely take that into account when looking to incorporate these in on your project. Today, we're going to talk about 4 projects in a case study. And if someone might mute themselves, it's getting a little noisy. Thank you. The catalyst is in a low seismic region, which is in the northeast of Washington State, and Framework, Mississippi, and Lincoln City are either in the Portland area or on the Oregon coast, so in a high seismic region. Now I'm going to walk through some of the prescriptive and performance-based lateral system options we have available to us as designers. Starting with the prescriptive code paths, we have mass timber shear walls here in Oregon. That's available with the Oregon statewide alternative method. We also have light framed wood timber shear walls, concrete shear walls, steel brace frames, concrete diaphragms, plywood or OSB diaphragms. One thing to note about the wood diaphragms is that currently code has some restrictions with how far the wood diaphragm can cantilever from your lateral system. Right now it has a 35-foot limit, and what that means is that your edge of slab cannot extend more than 35 feet from your lateral system. In this image, that would be the red lines that represent the shear walls. Reid will talk a little bit more about that later in the presentation as it comes with in relation to upcoming codes. Another diaphragm option we have is a steel plate to steel truss diaphragm. And essentially what this is a steel plate that gets fastened to the top of the mass timber panels. And you lay it out in a truss formation and you extend it out to that 35-foot dimension we were just discussing. As after that point, the wood diaphragm can pick up and do the work the rest of the way. Because the steel plate will be sitting on top of the panel, you will need a finish to cover it up, whether that's a concrete or gyp with a secondary topping floor finish on top as well. So moving on to the performance-based design code options available, we have mass timber rocking shear walls, we have mass timber shear walls with buckling restrained brace hold downs, we have mass timber pier and spandrel systems, and we have, of course, mass timber diaphragms available to us. So now that you know you want to design, to build, or develop a mass timber building and use it as its gravity system or lateral system, so what is that first step? So the first step we always recommend is that you meet with your local code jurisdiction. And during that first meeting, you will talk about the systems that you plan to use, you will discuss the prescriptive code paths that you will follow, and then you will also bring up any ideas that the team is considering that is outside of that prescriptive code path. And you'll use this initial conversation to really gauge that jurisdiction's level of knowledge of the mass timber products and these systems, and also their level of comfort with it. And you can use that information to really help make project decisions as you move forth towards permitting. If you do know you plan to use a performance-based design, you will also want to bring this up in this first meeting to get their approval to go down that path. So if you do want to use a performance-based design, what are the things that you need to consider, and what is the process? The first thing to acknowledge is that the schedule and the fees will be different from a typical project. The schedule will need to be a little bit longer, and the fees will need to be a little bit larger. And that is because it takes a little bit more time on the design side to complete a performance-based design, therefore more fees. And additionally, you'll need more fees because you have a larger team member, and that will include a peer review team. And the peer review team will include a geotechnical engineer and a structural engineer. We recommend that you start this as early as possible in the design process, ideally early in schematic design. Hopefully early in schematic design, you'll kind of narrow down what lateral systems and the structural system you plan to use. And once you know you need to go performance-based design, that's when you really need to start making these decisions and starting this process. Once you know you're going to do this, again, you're going to need to go back and meet with the jurisdiction. And during this next meeting with the code jurisdiction, we'll really set out what we call is the basis of design. And that's really kind of coming to agreement with them about the expectations and the process that you will do to complete the process to get the project permitted. You will need to evaluate if you need testing to be completed as part of the performance-based design. A lot of times with these new systems, you likely will need testing just because we're using the material in ways they have never been used before. Luckily for us, we have the Friends of the TallWood Design Institute to kind of lean on and connect us with these researchers who can help us with the testing that we need for our projects. And then once we get in contact with those researchers will help us create the testing program and identify the cost for the testing programs. It's also important to bring up that there are some times when you might be able to leverage testing that was completed for another project. That's not always the case, and you just have to ensure if you do leverage other project testing that the way you're using it is very similar to how it was intended to be used. Next, you will need to get ground motions, and this is what we will use in our structural models to replicate the earthquakes. The geotechnical engineer, as part of the design team, will be able to provide this information. And what we start with is we start with a response spectrum. And this is an example of a response spectrum for a performance-based design project. And what the geotechnical engineer does is they look at the seismicity of the area where the project is going to be located and the soil conditions, and they create what is called the target. And you can see that is the black dashed line on this graph in front of you. And so that is the target response spectrum that they're seeking. And then after they identify the target, they go out and get earthquake records from around the world, and they use that and then scale it to create what we call a modified motion. In this particular example, the modified motion is what is identified on this graph as the matched motion, which is that brown, red kind of squiggly line. And once we have that, they use that information to get us some accelerations and displacement velocity, kind of the orbital plot on the right-hand side, which is what we actually use in our performance-based design structural models. And I want to talk a little bit to the orbital plot on the right and why it looks kind of like a squiggly little, I guess, spaghetti meatball. It's because, when we do a performance-based design, we're actually modeling and looking at the building's performance in 3 dimensions. Therefore, we do need to represent the earthquake movement in those dimensions as well. So what you're seeing on the right is basically a 2-dimensional or a multi-dimensional input of the earthquake that we can put into our model. So as I was mentioning, there's a large structural analysis component to the performance-based design. Essentially, what we recommend or what we see is that it adds about 14 weeks to the design schedule. And during that 14 weeks, we will build our model, we will run the model, and we will evaluate the output. about 6 to 8 weeks of that time is actually just spent building the model, because it's quite complex. There's a lot of information that needs to be put into it to be able to really leverage that. The one thing when we're kind of getting close to that 4-week schedule, we kind of need to meet with the team and talk about, because it's really important that there's no changes that happen to the lateral system after that 14 weeks starts. So that means the wall locations need to be locked down, the openings in the wall, whether that is the door openings or mechanical penetrations, that needs to be done prior to starting that 14-week process. And if something changed, just means we have to go back and change, and we lose time, and therefore have to potentially add time to the schedule, which is not ideal. As you can understand, that pushes a lot of design effort to happen a little bit earlier in the design phase than would happen on a typical project. So that needs to be just understood by the whole team when you're, going into a performance-based design. So this is an example of a structural model that we would be creating for performance-based design. This is actually the model for the framework building that was used. And it's actually currently in its deflected shape. So it's actually has moved in 3 dimensions from an earthquake force. And you'll see lots of lines and dots. It's hard to see the shell elements in this image, but there's some shell elements in there. And even though it looks quite simplistic, there's actually a lot of information that is built into this model itself. So each one of those dots and lines and connections, we have put some information about how the building will perform into it. And we use the research that might have been done or other research that we know about those components, and we put that into those components. And that really helps us replicate and understand the behavior of the building as we run through our structural analysis. A couple examples of this information that we put into the model include how does that shear wall panel perform as it undergoes an earthquake? What happens at the base of your rocking mass timber shear wall when it kind of crushes and deforms again as it rocks back and forth? And how does the splice connection between panels work as it cycles through the earthquake? So a lot of information gets built into that. We run through the earthquakes and we take out that information and use it to complete our structural designs for permitting. The last thing to mention with regards to a performance-based design process is that it will require a longer permitting process. And that is in general just because of the complexity of the work that takes place and therefore that they need to review and approve. So it's just something, it's an important thing for the whole team to be aware of when going down this performance-based process. So with that, Jack, would you like to share us with some project case studies?
Yes, thanks, Katie. Okay, I'm going to share my screen here. Alrighty. So yeah, now that we've heard a little bit about the process that goes into creating one of these buildings using a mass timber lateral system, we'll talk about 3 buildings where KPFF has actually done this process. And I'd like to start with the Catalyst building. So this is a project that was recently completed over the summer. This is one we did with Michael Green Architecture in Katera. It's 160,000 square feet of type 4 HT construction. It's going to be used for office space and higher education. So getting into the lateral system, we're using CLT 7-ply shear walls coupled with buckling restrained brace members as the hold down devices for the primary lateral. Diaphragms consist of CLT floor and roof panels connected with steel plate strapping. And because this lateral system is a little bit unique, using the BRBs as the hold downs, we pursued the alternate means and methods code path. So we worked with the city of Spokane, where this project is located, to outline our design criteria, the design process that we plan to use, and identified any additional testing that would be required to justify the design. If we look at the floor plate, the building has a 30-foot by 30-foot typical grid. One of the goals for the design team was to keep all of our shear walls towards the center of the building, keep all of our perimeter bays nice and open, nice and flexible for future occupant use. So we contain all of our shear walls towards the center of the building. We have 3 shear wall cores around the stairwell shafts, as well as 5 standalone shear walls oriented to that north-south direction. We look at an elevation of one of those typical standalone walls. We can start to identify some of the different components that was used. So each wall panel, because it's roughly 14 feet wide by 70 feet tall, we needed to break it up into 4 separate CLT panels. These are identified here at the red lines. The panel joints have a half-lap spline connection along the vertical length, as well as a epoxy threaded rod for the horizontal connection about halfway up the building. Then at the base of these shear walls, we have our BRB hold downs. So BRBs are typically used in steel frame structures. As engineers, we really like them because they have a very reliable performance. They yield in compression and tension at approximately the same values. And so for this shear wall design, we're concentrating all of our yielding and ductility to these BRBs, while the rest of the shear walls remain essentially elastic. So when we go to model and design all these buildings, as Katie mentioned, a lot goes into the modeling. So we need to identify all of our panel, all the panel sizes, the stiffness of each panel, stiffnesses of the spline connections and joints between panels, as well as the stiffness of our BRBs. If we look at an isometric view, I've kind of stripped down everything in the building here except for our shear walls so you can get a feel for the geometry. So each of the walls has a BRB down at the corner, the bottom level. And in addition to that, we have 3 cores. So we went with the core configuration because with the core shape, when all 4 walls are able to act together, they act a lot stiffer and stronger than if the walls were separate. The cores also allow for fewer BRB hold downs as if they were separate, because we have 4 per core as opposed to 8 would be required if the walls were independent of each other. But the cores required us to really understand this corner connection a lot better. This is a fairly unique application using the core shape. So we needed to justify this connection in terms of the stiffness that is relayed across these panel joints. So we came up with this detail with a screwed connection, built some specimens, and then we're able to test them at full scale down at Oregon State. So here you see one of these specimens in the lab where we're using an actuator to apply a shear force across panels. This way we're able to capture the behavior of the connection, understand the stiffness and strength here. Now here's the ultimate failure once we just blew this thing out of the water, right? So the failure mode for this connection have these screws that actually pulled through the wood and yield in a very ductile way. Now in a seismic event, this would never happen. We would design this connection to stay essentially elastic while all of the deformation and ductility is provided by those hold downs. Getting into some of the construction photos, here's a shot taken at the ground floor where we see the vertical BRBs installed on one of our cores. One of the tricky connections that we had to come up with was how the BRBs actually connected to the CLT shear wall. So we were able to leverage some of the connection testing that was done for the framework project that Reid's going to talk about, which used the fully threaded rods installed into the end of the CLT panel. So that's what we see here, that those threaded rods are drilled and epoxied quite deep into the end of the panel to develop the strength of the BRB. And just for reference, we're talking in the range of 200,000 pounds for these BRBs. So that the load is quite high, much higher than you would see for a typical wood frame building. Now, as I mentioned, since our building is 70 feet tall, obviously you can't get panels fabricated and shipped in that length. So we introduced a horizontal splice joint between panels about midway up the building. So this photo shows the lower shear wall panels already installed. If you look closely, you can see some pre-drilled holes. And those are going to be ready to receive the threaded rods that get installed down to the lower panel and up into the panel above. Now, obviously with our stair cores, we need door openings at each level. But in order to maintain the strength of a core configuration, we added these steel plates around the door openings in order to transfer forces around the openings, while still maintaining the stiffness of that core. And then last photo here from the Catalyst project is just a photo kind of identifying some of the typical elements you might see with a CLT diaphragm. So if you can see my cursor, we have CLT floor panels, obviously, with plywood splines between each of the panels. Those transfer in-plane shear forces, as well as light gauge steel plate strapping connecting the panels. So the next project is the Lincoln City Police Department. This is a smaller building we did with FFA architecture out in Lincoln City, obviously. The lateral system uses CLT shear walls above level 2 and concrete shear walls in the level below. We used the CLT panels at the roof as the diaphragm system. And for this project, we pursued the Oregon statewide alternate method 1501 as the code path here. Now, it's important to note that while that's a prescriptive approach, it is rather conservative in how we need to calculate our forces. So one area where the code I think is going to catch up in the next couple of years or so is identifying CLT as a more widely used material in lateral systems, and it's not going to be as conservative. Reid will touch on that a little bit later on. So here's a shot of the exterior of the building showing some of the CLT walls used on the outside faces, as well as the CLT roof panels currently being placed. We step inside of the building. You can see that the steel frame supporting the roof panels, but again, our CLT panels are on the exterior. One of the unique details we came up with for this project was at the hold downs again. So the photo we're looking at shows a steel plate installed onto the end of the shear wall panel. That is fastened from the steel plate to the wood with inclined fully threaded screws, both in the upward and downward direction. So next up here, in the last project I'm going to talk about is the Mississippi Mixed Use Building. This is the architect for this project is Vector Architecture. It's located here in Portland and is currently under construction. The lateral system uses CLT bearing and shear walls all around the perimeter of the building. The CLT floor and roof panels serve as the diaphragm. And again, we pursued the Oregon statewide alternate method 1501 as the code path here. So this is just a recent photo taken during construction. Obviously working on the foundations here. I think the mass timber is expected to arrive on site in the next couple weeks, and I'm sure it'll be up before we know it. Looking at the floor plan, there's 2 wings of the building connected by a hallway, and which also houses some vertical services, such as stairwells and elevators. All of the red lines shown here represent the shear walls that also serve as the gravity-bearing walls. we look at an elevation of one of those exterior walls, you can see there's quite a lot of window openings here. So there's not a lot of solid wall for us to use as our shear walls. So it's really more of a pier and spandrel type system where the CLT panels are solid for the full height of the building between window openings. And then there are spandrel panels above and below the window and door openings. Now, all those panels are connected together using steel plate strapping, similar to what we saw in the Catalyst project for those cores above the doors. And then at the base of our piers, there are hold downs at each end, much smaller in this case because of the quantity of those piers. And then lastly, the thing I wanted to point out with this is, even though there's a prescriptive code path to get these buildings approved, there's still some challenges for us on the design side. So this is a shot taken of our analysis model showing how each of those wall panels needs to be modeled, each of the joints, all of the plate strapping. And it's a bit more detailed than what we would typically do, say, if this were a late stud framed building. So just understanding that there's more on the design side, there's also more on the review side. I think our engineer who worked on this project actually ended up sitting down with the code reviewer, getting them comfortable with the design and the building before really getting the actual permit in hand and moving forward with the project. So with that, I'll stop sharing and I'm going to turn it over to Reid, and he's going to share some information on framework and some cool testing.
Thanks, Jack. Yeah, let me bring this up here. So as Jack mentioned, I'm going to talk a little bit about framework as kind of our last case study for today, and then transition a little bit into recent testing as well as some upcoming code changes. So framework, I think most are aware of the framework building. It was a project led by a great team at Lever Architecture, also included Walsh Construction and Structurecraft, and many others. It was one of the winners of the US TallWood Building Prize competition, and unfortunately was not built. It got to the point of receiving a structural permit, but the decision then was made not to pursue construction. It's about 140 foot, would have been about 140 foot tall building that uses post-tension rocking shear walls. It would have been the first of its kind in the United States, along with energy dissipators. And I'll talk a little bit more about sort of the full components of the system that was proposed for framework. Additionally, the diaphragm was going to be untopped. So it was going to be using the CLT as the diaphragm itself for resisting seismic forces, and with, similar to what Jack has showed, steel plate cords and collectors. And yeah, again, it was not following a prescriptive path, instead following the alternate means and methods or performance-based design path. So this is a typical framing plan for framework. In red, kind of you're seeing all of the CLT rocking walls, and as we see this commonly as we're looking at mass timber lateral force resistance systems going taller, that we're trying to concentrate those elements around the vertical circulation area, so the stairs and the elevators. And you're starting to see the creation of a core configuration, even though it wasn't to the degree that we pursued for Catalyst. And then in blue is just showing cords and collectors. So describing a little bit better what the rocking wall system was envisioned for framework, and something that I think has a lot of legs on future projects, is the idea of instead of fighting the inherent nature of a CLT panel to want to rock up and over, is you sort of use it in its best way. In that, you essentially can take the CLT panel, or the CLT panel that forms the wall, which is inherently stiff and strong, and you use either internal or external post-tensioning to hold that wall down. That provides you a recentering capacity so that after the earthquake, your building will right itself and come back to center. Additionally, for framework, the idea was to place a glulam column, which we call bounding columns, at either side of the wall, and connect between those bounding columns and the CLT panel, the CLT wall, energy dissipators. So those energy dissipators can be many different forms on projects. On framework, we were envisioning what we call UFPs, or U-shaped flexural plates, which is just, it's a steel plate that's bent into a U. So as the wall would rock up against, up past the bounding column, it would cause these U-shaped flexural plates to bend, to roll, and in that way dissipate energy. That video you're seeing is from Portland State University, actually not for the framework project. Portland State University has done a decent amount of research on UFPs because they're used for other applications, but that kind of envisions how they work. So framework was very early in the development of mass timber lateral force resisting systems. So at that time, we didn't know what you would think of a lot of basic things about mass timber in applications for seismic zones. Starting with it, I'm going to just kind of zoom in on different portions of the lateral force resistance system and talk about them in more detail. So the panel itself, there was a lot of question of the panel itself about what the in-plane shear stiffness was of CLT panels. So a lot of research has been gone into out-of-plane stiffness, flexure and shear, rolling shear of CLT panels, but not as much on in-plane stiffness. So we worked with Oregon State University to devise a test setup that's shown here, and take CLT9 panels and put them in 3-point bending and cycle them. And in that way, be able to measure what the real shear stiffness is, which is surprisingly tricky thing. We took the panel to failure also. So ultimately what that boiled down to was a representation of what the shear stiffness is versus shear stress. And then we were able to compare that against some of the closed form solutions which exist in literature at the time to estimate that. And this is one of those inputs that Katie was talking about that feeds into the analysis model. So jumping back and looking at a different component, now we're going to zoom in on the splice of the wall. So again, splicing CLT walls, just like Jack was discussing with respect to catalysts, when you have a building that's basically over 40 or 60 feet, you can't get a panel that long, so you need to be able to splice it, and you need to be able to splice it for fairly significant shear and moment demands. So we again worked with Oregon State University to introduce, you're seeing there on the right-hand side in red, splices into that panel setup that we tested very well. We're now introducing splices into that same setup. We tested several different connection types, and the one that was ultimately chosen, Jack discussed its application for catalysts, sort of a way we were able to leverage the framework testing for catalysts. And this is showing a sort of a picture of that test with the splice here shown here. And ultimately, again, because it's of interest, not just for the project, but more globally for other projects and for research, we took the panel to failure. Here's a photo well past its acceptable level. But that's part of the fun part of testing, as many on the call now. Now zooming in a little bit to the toe of the wall. So the wall is under uniform compression from the post-tensioning. As it's rocking over, that compression shifts to the toe or the leading edge of the wall. And that tends to, by concentrating that compression, tends to concentrate the crushing in the wood. And so there's a lot of research has been gone into the performance of CLT or the compression capacity of CLT in terms of force, but not as much into what happens post-peak, meaning what happens when you get into the plastic strain region. So common theme here, we worked with Oregon State University to develop 3 different specimen types and put them in uniform compression. The first was just a chunk of CLT5 that we were going to crush. We then put in screws, to the idea being to help prevent the outer lamination from buckling, and then also plating the end of it or armoring the end of it to provide some akin to concrete confinement, but for wood. So this shows the test setup, a very simple pure compression test, and again on the right, far beyond acceptable performance, but kind of indicating the failure modes that you would, the eventual failure mode of the CLT and crushing, and then again translating the mountains of data into something usable for our analysis model. In this case, it was a stress versus plastic strain curve. So another component of, we're talking about lateral force resisting systems, but we'll have the whole gravity system that needs to go along for the ride, often referred to as deformation compatibility. So we were interested in looking at, for framework, that connection there, which is a beam to column connection that has a ton of constraints, seeing pretty moderate to high structural loads, shear primarily. It has aesthetic constraints and architectural constraints about wanting the connection to be concealed and have a really clean look, and has fire constraints around, in our case, achieving fire ratings. So, but what happens to that very tight joint when it has to go through the deformations or the story drifts expected during the earthquake? That was a question we had and couldn't really find a good answer to it in the existing research. So we developed a design of a connection that we felt could handle that imposed drift and deformation, and worked with, you almost guessed it, this time Portland State University, to test full-scale beam column subassembly. So I'm going to show you a quick video here of what that looks like. So this is going to be showing on the left panel the full view, a time-lapse view of the subassembly being worked. On the bottom right panel is a close-up of the joint. And in the top right panel, you can see essentially it's a spring that we've created using Belleville washers that keeps the beam from unseating. So as the gap forms, it then gets closed by this, this spring. And we went out to actually 6% story drift with this, with no loss of capacity and pretty much almost no damage. So one final thing I want to talk about in framework is the connection between the diaphragm and the wall and how that accommodates the upward movement of the wall. So I think you can appreciate a rocking wall, it rocks up as well as translating over. So if it were to rock up, the diaphragm would have to come with it if there was pure connection between the two. So the idea being that you create a connection which allows the vertical movement and actually the rotation of the wall. There's uplift and rotation occurring simultaneously without lifting up the diaphragm and potentially damaging it. So this video I'm showing is from actually the NHERI 2-story test, which you're going to hear about in a couple of weeks at the next meetup, showing the performance of this tongue connection, this diaphragm to wall connection. As the wall, you can see here, I'm hearing lots of sound, but you're not. As the wall is rocking up past the floor, no connection really between the floor and the wall other than this strong tongue connection, which basically transfers horizontal shear, but no other forces or minimal other forces. So that talks a lot about the research that went into framework. And I think, you know, even though framework wasn't built, a lot of that research has become useful and will continue to be useful for projects going forward. I also want to talk about some other recent research, specifically the NHERI project, which you're going to hear about in a couple of weeks. So I won't belabor it too much. I'll just show a little bit of this time-lapse video of the 2-story test. And I'll let Professor Pane in a couple of weeks talk more about it. But the idea being that we were able to place a 2-story specimen on the shake table at UC San Diego and shake it through many, many, many earthquakes, probably longer than human consciousness can even understand for a real building. And it performed exceptionally well. This is just showing it going up and going up actually quite quickly, which we all know to be true for timber buildings. Okay. And the next evolution in the NHERI TallWood project is now, again, I hope Ling in a couple of weeks shows you this video again, because I'm just gonna talk over it and not let you appreciate it too much. But we're gonna, on that same shake table in 2021, we're gonna put a 10-story. And you'll see, if you look closely, there's a lot of similarities of this 10-story to framework, and that's not a surprise to those involved. Moving things along, I'm running out of time here. I want to talk about another project, which is just a teaser for a presentation in a couple of weeks, which is the Pier and Spandrel system that we have been working with Oregon State University in developing. The idea of the genesis of this Pier and Spandrel project is looking at ways that we can use mass timber to retrofit unreinforced masonry buildings in historic downtowns, and ways in which, rather than using a wall, which would obstruct the obstruct the windows or obstruct the views and disrupt the historic character, could we find a way to sort of mimic the Pier and Spandrel look of these older URM walls, URM buildings with mass timber? So again, this is just a teaser showing a test that we conducted 2/3 scale at Oregon State University of the Pier and Spandrel system, which is essentially just big beams, big columns made out of CLT with ductile steel connections, kind of interesting ductile steel connections that we devised in it. And I'll let that'll just whet your appetite for the presentation to come. I won't steal their thunder. One other thing that I know OSU has done a lot of research on and we're finding of interest is mass plywood panels. And so Katie said at the beginning that from a code perspective, they're equivalent. They're both certified under PRG 320, but interestingly, they're not exactly the same. So, which should be obvious. So this is a quick comparison. You don't have to look at all the numbers, just look at these values. This is sort of a place I like to start when I'm thinking about using CLT as a lateral force resisting system as compared to using concrete. So when you look at the flexural stiffness of CLT for the same wall thickness, for the same length, and the shear stiffness as compared to a concrete wall, you've got about 50% of the flexural stiffness, and you only have like 5% of the shear stiffness. So a CLT wall building is more flexible, or alternatively, for the same target drift level, a CLT wall building will need longer walls, assuming again that the floor masses are the same, which is not, if you have a concrete building versus a mass timber building, you get a large benefit there in terms of the mass of the structure. But for the same floor mass, you're going to need more CLT wall than you are for concrete. And so that's a hard thing to grapple with as you're laying out your lateral force resisting system, and it becomes an issue for costs of fiber and all sorts of things. So interestingly, when you start to look at mass plywood panels and do that same comparison, but this time we're flipping a little and we're ratioing the mass plywood panel stiffness to that of CLT, we see that the mass plywood panels are about 150% as stiff flexurally and shear, in flexure and shear as CLT. So what that really means is for the same, they're not equivalent. If you had and you were just concerned about stiffness, a mass plywood panel would allow you to use less wall, or it would allow you to have lower drifts for the same wall length. And so I think we're going to see a renewed interest in mass plywood panels for lateral force resisting systems going forward. So a quick note about upcoming code changes. The first one is with respect to platform framed mass timber shear walls, kind of similar to what is shown here. This is sort of the next evolution of the Oregon statewide alternate method. The Oregon statewide alternate method allows you to design these walls prescriptively, but with an R of 2. This is now going to allow you to design these with an R of 3 to 4, depending on their aspect ratio. So it's a little ways out. It just received approval a couple months ago from the ASC 722 Seismic Committee. So that means it will be published in ASC 722. That's still until 2024 IDC before it gets adopted into the International Building Code, and then ultimately into the Oregon Structural Specialty Code a year or two later in other states as well. But we see, even though it's not necessarily available at our right in the code yet, We think that as soon as we see ASC 722, which, seeing how things are going, 2022 will be here before we know it. When ASC 722 is published, being able to, I think, take that to jurisdictions as a performance-based design light, meaning you're going to follow the prescriptive procedures, but you're still going to have to invoke an exception to the building code. I think there's going to be legs to that. We do see, even though it's not the rocking wall system, it's not a super high ductility system. So I think we're still going to see it most applicable to those buildings which already have a high wall density for other reasons, for apartment buildings or so on. And then in mass timber diaphragms, untopped mass timber diaphragms, Katie was talking about, so, this limitation of 35 feet cantilever length. And so untopped mass timber diaphragms are approved by the AWC committee. So they're going to be in this bid whiz, but not for some time. They're going to be adopted in the 2021 IBC. So it's a little bit more imminent. But I think it's going to drastically expand our ability to use mass timber diaphragms prescriptively, something I think that we've all kind of recognized, that CLT diaphragms aren't light frame diaphragms. They should be able to span farther. They have way more capacity. They're much stiffer. So I think that's now going to be reflected or is being reflected. And this also will allow you to cantilever longer and farther than 35 feet with a CLT diaphragm. So with that, I think we're going to open it up to questions in a minute. I think just to recap a little bit, Katie brought us a little through sort of how you would go about setting things up at the beginning of the project and choosing this path between performance-based or prescriptive. And we kind of showed a couple examples, both of where we've been using the prescriptive path, the Oregon State Wall alternate method, as well as the performance path. And I think you can kind of see where the applications of each of those paths fall. There's a lot of research that's happened, is continuing to happen, that's pushing the industry forward. In the next couple of years, really, performance-based design is probably still our best path for getting for designing sort of innovative mass timber lateral force resisting systems, but there are options for doing a prescriptive path, and there are right buildings for using that prescriptive path. And it's something that we're really excited to share with you all. And let's open up to questions now.
Great, thanks. Before we open up the questions, I just want to quickly mention that we have some questions in the chat. So if we hit a lull for any reason, I'll read those out loud. Thank you very much, Reid, Jack, and Katie. Amazing presentation. I'm going to open it up to general questions now, and I just wanted to let anybody know who's interested in the future meetups, including the seismic research meetup. You can find out information. I'm just going to post a link here to our last newsletter. You can find out whatever you need to find out there. So, all right, with that, please feel free to ask questions directly, and we'll take it from there.
Katie, do we want to start with the chat ones and then?
Yeah, we can definitely start there and then kind of see what questions come. So I think the first one, Reid, I'll pass to you, is what software has been used for the performance-based design?
Yeah, so there's the mass timber lateral force resisting systems. If you can condense the performance of them down to the same kinds of concepts that we use for other systems. So the existing tools that we have work okay in terms of doing performance-based design, but now with mass timber instead of concrete or steel. So what we have used in our office is either SAP 2000, which is a computer structure product, or Perform 3D, which is also a computer and structures project. Those being kind of the bread and butter of software packages that are used at least in the US. Great,
thanks, Reid. One of the next questions, Jack, will kind of move to the catalyst core. I think there was a couple of questions to that, so I'll field these to you. So the first question was about the coverage of that core, and does it get furred out and covered? And then I think there was a second question maybe about the fire rating, and if you could maybe speak to that a little bit as well.
Yep. Yeah, so the exterior of the stairwell cores were furred out and gypped. The interior of the cores were left exposed, and we did design those shear walls for a 2-hour rating in terms of it for the gravity load case.
Great. And I'll pass these other ones to you as well, because there's a lot about the BRBs, So the BRB, is a buckling restrained brace. That's what the BRB stands for. Thank you for the chat for helping clarify that question. So Jack, to you, just kind of talking about why we used it and how it's important as an energy dissipator, damper. Some other questions about the BRBs, about like, were you able, when you use the BRBs, you're able to get smaller hold downs instead of using them as fuses. So kind of talk through why, perhaps.
Sure. So I think the main intent for the BRBs was to use it as a fuse, right? So all the yielding and ductility is concentrated within the BRB hold down when the wall wants to rock over, right? And then the rest of the wall panel and the panel connections remain elastic, and they don't yield and they don't fail. So by using the BRBs, we have a better understanding of when that BRB is going to yield, so that we design the rest of the connections for a lower force level than we would have to if it was, say, like a regular steel plate hold down. Did I hit most of those questions?
I think so. Yeah, I think so. I'm trying to kind of combine a couple of them. Please, if anyone wants to have a follow-up question, we can always jump on that too. I think the next question in the list was a question about wood diaphragms. And are the typical ratios for wood diaphragms and shear walls used in CLT, are they similar to what is a wood sheathed wall? I would say that's a little kind of unclear in the code, considering the code doesn't currently identify CLT as an appropriate wood diaphragm. So right now I would say jurisdictions probably lead you towards using those typical ratios, but we know as designers that you can kind of go beyond that. We just have to work with them to kind of get them to accept kind of how we know these systems can be pushed. Definitely from a shear wall standpoint, I don't think we're restricted to those ratios. Ben or Jack or Reid, feel free to jump in and add on.
Yeah, I guess I'll just say with respect to wall panels, generally we see, so in rocking wall systems, we generally see aspect ratios not being too large for framework, which is much taller. It was like 7:1. So it was what I'll call a high aspect ratio system, but it can work just well for in different configurations. Not, I guess what I should say is for a rocking wall configuration, it starts to become a little more difficult when you're at a low aspect ratio, because it tends, as I think as you can appreciate, as it gets shorter, it tends to want to slide more than it wants to rock. So depending on the type of system, you're going to see different aspect ratios. Because we're not prescriptively held to any of those aspect ratios, when we're doing performance-based design, really the sky's the limit. But with respect to rocking wall systems, sort of there is a sort of a need to look into higher aspect ratio. And I guess just to add on to that, for the new platform framed wall system, there are aspect ratio limitations, and those aspect ratios actually govern the R value that you can get. So higher aspect ratio, you get a higher R, lower aspect ratio, you get a lower R.
Apartment number 162.
Great. So Reid, I think I'll pass to you the next question, which is about, is there a cost to capacity ratio better for a post-tension rocking shear wall or a CLT shear wall BRB hold downs? It's kind of an interesting question for sure.
Yeah, it's a great question. I don't think we have the answer to it, to be honest. We're presenting a couple case studies of fairly drastically different building types. Catalyst being much more in the open, so to speak, and framework which was not built but would have been built downtown Portland. And then there's also, I think, a need for more cost data over more than just a couple projects to really answer that question effectively. I think I will say that one of the reasons one of the reasons was cost, that framework wasn't pursued, and framework wasn't the code conforming building that wasn't just sort of a simple seismic performance minimum building. There were a lot of enhanced objectives, didn't have time to talk about today. And did those lead to cost increases? Almost certainly, yes. So unfortunately, I don't think I can answer the question and say what the right cost to benefit ratio is, other than it's got to be studied project by project to date.
Great, thanks, Reid. Okay, this one is about the Pier and Spandrel. Question is, for historic URM buildings, concrete can be used for retrofits. What are the advantages, specifically structural, to using mass timber over concrete for these applications? Reid, do you want to continue?
Sure. Yeah, so I think that the idea behind the Pier and Spandrel project was, could we find a way to use materials which could be placed by, let's say, a less sophisticated contractor, or less sophisticated workforce. So not to say that it takes extreme complexity to do a concrete retrofit, but if you're doing shotcrete or casting inside of an existing building, definitely a tricky thing. So the idea with the mass timber was really motivated less by a structural demand as by maybe an aesthetic and a could we envision something for a little bit more rural communities, and also just something along the lines of, could you take materials which are common to those smaller communities like wood and allow them to be used? Carpenters in that area obviously familiar with wood and maybe not as familiar with shotcreting. Is there a structural benefit? I think there can be, but you need to really just think about how the system is envisioned, where and again, I didn't go into it in depth, so I can't explain too much, but we essentially wanted to use fuses that could be unbolted and bolted back in, so that you could have a system which was resilient. You could do that in concrete. It would be a little bit harder.
Thank you, Reid. Jack, this one I think is regarding your catalyst diaphragm, and I guess if you could talk to the steel strapping and that design.
Yeah, so again, because it's the alternate means and methods, we didn't follow the prescriptive code path of following the diaphragm design guide and the NDS per se. So we actually use forces from the ASC 716 that were intended for precast concrete diaphragm, so that theory of the CLT panels are pretty rigid, and that most of your deformation and ductility is coming from connection between panels. So that's where we got our forces from, and then just kind of using basic mechanics, that's how we designed the steel plate strapping to ensure the forces got into our cores.
And a lot of those steel plate strappings, just to add, are kind of the cord elements in the diaphragm to kind of provide tension across the top of the wood panels.
Exactly.
Okay, so the next question is, what's the affordability of mass timber testing? Seems like that could be an obstacle for most clients, especially public buildings. So Reid, since you've been involved in a lot of testing, obviously I'd also open it up to the TallWood Design Institute to speak to this as well, as there's a lot of researchers on the call. So
yeah, I can start things off. I mean, I think that's absolutely an obstacle, especially for, I would say, absolutely public buildings, but also smaller projects where you can't absorb the fee that's required for testing in the construction cost. I think that's where things like this are great, in that we're trying to share what testing has existed and ways in which it can potentially be leveraged on future projects, so that it's not just a project-specific testing doesn't just become project-specific testing, it transcends the one project. And I think that the other thing, I'll make a quick plug for the KeyCats consortium that KPFF and many others have joined. I think that's the idea, is that not all of us individually can't can't do the testing alone, but when we pool resources, we can get something that's more than some of its parts. But if TDI would like to jump in here, and speak to this question, I'm happy to let them answer as well.
Yeah, thanks. I'm not sure if Ian's still with us. He can speak best to the CCATS consortium, but Andre, I don't know if you're here either. Maybe you want to speak to that a little bit, the intention.
Hi. Yeah, I've not much else to add. Thank you, Reid, for the plugin to CCATS. And yeah, it's a new consortium that we're putting together, and it is going to be industry led, and it's bringing in a lot of the questions that research can answer, but it's questions from industry, things that need to be answered soon now. And by working together, the different members will be able to pitch what are the most prevalent questions that need to be answered quickly. And then TDI with the testing will help with that. In terms of testing for bigger projects and for things like framework, sometimes these are not cheap, but for example, Reid showed a few examples of there's a lot of fabrication, there's technicians involved, there's people involved in able to get the product and the results that are needed. So yeah, it's very much project specific, and we're glad to be here and to help industry as needed.
Evan, in lieu of Ian, I thought I would add that we have funds we get every year from the Agricultural Research Service that we give out competitively to our faculty, as Andre knows, to do research projects. And sometimes when we're approached by industry about a certain project, we try to connect them to a researcher or a team of researchers to see if we can make a connection where they can make a successful proposal. The proposals are competitive. We can't award everyone. We have an outside group of experts. A number of people on this call have been some of those experts who actually rank the proposals. But we have a number of ways of using both public funds. The ARS money comes from the USDA, as well as the CCATS consortium to help to fund those projects.
A number of other grants as well. I mean, we had an EDA grant that was used for the seismic retrofit testing, for example. So there's kind of a number of financial resources that can be kind of compiled to make certain types of testing possible. Just want to add that.
Wonderful, thank you for chiming in. That was very wonderful. Jack, I'll pass this one to you. What R factors are allowed to be used for the BRB CLT walls and also post-tension CLT shear walls? So maybe we can chime in regarding the post-tensioned, but this would be probably a catalyst.
Sure. So yeah, with a performance-based design, you wouldn't use an R factor because you're actually inputting the ground motions directly into the model. So it's a little bit different than if you're doing, say, a response spectrum or an equivalent lateral force analysis. So yeah, I think on the Catalyst project, we backed out what our R factor would be, and it was somewhere in the range of 4.5 to 5. So to put that in perspective, the statewide alternate method makes you use an R of 2. So our forces on Catalyst were less than 2, factor of 2, what we would have had to use if we went with like the statewide alternate method procedure.
Yeah, that's a great point, Jack, is that even though we don't use an R factor specifically in performance-based design, we have to start somewhere, right? And what does some of the performance-based designs that we've done tell us about where these systems, where the sweet spot is for those systems? So yeah, for something like a shear wall with BRB hold downs, you probably could justify the equivalent of an R of 5 to 6, maybe even as much as 8, if you consider that a BRB itself, as in a brace frame, could use an R of 8. And then for post-tension CLT walls, we've kind of taken an emulative approach of saying these are similar to a post-tension concrete wall, and a post-tension concrete wall can use an R of 6. So we feel that it's fair to use also on R6, but ultimately it all has to be borne out in the performance-based design at this point.
Great. Okay, another catalyst core brace frame or BRB question about whether it was exposed, painted, or if it didn't have to have any coating.
The BRBs did not have to have any type of fire protection because they were only there for the lateral system. They weren't providing gravity support.
But they were eventually enclosed, right? They're not, if you walk into that building, you won't see them. Is that right? Yeah.
Yep, they're exposed.
Oh, they are. Okay, I forgot that. So you can come and see the structure.
Yeah,
we love
cool.
it. We love it. Cool. Okay. So Hans, I think, had a comment about CLT diaphragm design methods. Hans, did you want to, open up the mic and ask your question?
Sure. Hi. Yeah, just real quick. Thanks for the presentation and hats off to KPFF on Catalyst. I work for Katera and just see the project to get all the press earlier this week from opening, and it's wood from the ground up. So the CLT shear wall, pulling that off was really cool. On diaphragms though, just to have interested people on the call find other resources. The Structural Engineers Association of Washington has a white paper that they published several months ago on getting a way to engage your building official on how to use CLT in a design method. It does address things like the 38 foot maximum cantilever span. And it was mentioned about the NDS coming into 2021 IBC with, or 2021 SPIDWIS with a design method that's true and I think super important. If you have a project that's underway and want to find out more about that, I sit on that committee and would be happy to help connect the dots. The challenge there is on the white paper and other design methods playing, I'll say conservative day one, is they're looking at potentially using the alternative diaphragm approach in ASC 716, which ramps up your force levels, but the ductility factor that's built into that is still 1.0, which creates a delta. And within that document, there's a requirement that your panel-to-panel connections still be group 3 S or group 4 failure mode. So you're still looking for ductility in the panel-to-panel connections, but your force levels are really high. So where we are, where we were in that committee completed the work before the NDS committee completed their work was the right place to be, but there's better knowledge and even testing knowledge around that design method. So I think that's just really important because I'm a practicing structural engineer and you can only do what is out there in sort of consensus-based design method place to really practice in the US and feel good about what you're doing. So there's all this sort of every month a new chapter unfolds in mass timber and what we can do. So that's what makes it exciting.
Thanks for that background, Hans. That's good stuff to know.
Definitely, thank you. Reid, you were waiting for this question to come up, so do I need to repeat it?
Yeah. Eric McDonald was asking me this on the side too, and yeah. So the picture behind me, I think this is also a question from Patrick. The picture behind me is actually a wind tunnel. So they built this wind tunnel out of CLT, and wind tunnel basically you create tiny versions of buildings and you put it in there and then turn on that huge fan that you can see there and basically simulate wind. So we had a project, was not a mass timber project, that they were doing wind tunnel testing of. And so I showed up and I was like, walked into it and I was like, wait, this is CLT. You built your wind tunnel on CLT? Very cool. So yeah, I'm glad someone asked.
Can be used in many applications, right? So Reid, another question regarding the URM. Okay, So regarding URMs, the mass timber solution would likely be less additional load on the gravity systems and foundations of the existing building. It's also a much cleaner trade than concrete or shotcrete dry trade, as opposed to a wet trade, which could be preferable in a phased or occupied renovation. So thank you, Patrick. Those are all great additional comments. I don't know if you want to, sounds like you have a lot to say. Feel free to open up your mic and, you know, expand on it any more. But I mean, yeah, definitely all benefits to using mass timber for that retrofit.
Yeah, I think the idea actually is that you could potentially cut a slot in the roof and lower the whole mass timber pier and spandrel system down, if it was at the exterior of the building, down with a crane into it, which would be hugely beneficial if the building was to be occupied during construction, because you just need to basically cordon off a small area, as opposed to shotcrete, which is messy and disruptive.
Great. Okay. Another follow-up question for the performance-based design was a pushover analysis or time history analysis used. So this would be to the framework and the catalyst. So Jack and Reid.
Mm-hmm. So for catalyst, we used a pushover analysis. We felt that with the project being in Spokane in a lower seismic zone, that a full time history analysis wasn't really required to justify the design. So that's why we went with the pushover analysis.
And for framework, we did a response history analysis. Really, like Jack was saying, sort of the height and the seismicity of catalysts lent itself to a nonlinear static or pushover analysis. Framework being much taller and having significant higher mode effects, a static nonlinear static analysis wouldn't have been as appropriate.
Great. And then the last question we have in the chat is, would like to know what the typical effective damping ratios you have used for UFP rocking CLT and BRB CLT solutions.
Oh, that's a question from Tu. Hey, Tu. Yeah, so we don't, a lot of times we're not explicitly calculating what the effective damping ratio is when we're designing these systems with either UFP, some kind of energy dissipation device. For rocking wall specifically, we're actually more looking at the ratio of rocking capacity that comes from the energy dissipation devices as compared to what comes from the post-tensioning. And you do that because you want the moment capacity or the capacity from the post-tensioning to exceed that of the energy dissipation devices. If you don't, then you don't have enough post-tensioning to recenter yourself. And so when a rocking wall where you care about recentering, that's an important consideration to balance those. And usually what that ends up meaning is you're getting 10 to 15% effective damping as kind of a rule of thumb. We're not necessarily expressing it that way, but that's how it would be what it would end up.
So those are all the questions in the chat. Like Evan was saying, we can definitely open up your mic if you have other questions that you want to ask. Feel free.
We have a question from Lek here.
Great.
Lek, you're muted.
It's rather a comment than a question, following up on Judith's comments, and a little comment to Katie's outline of projects. I cannot stress more how important is your early engagement with the CLT manufacturers. They either have their own engineers on board and architects, or at least they speak engineer and they speak architect. They can customize the properties of panels produced for your project. The earlier you start the conversation, the better you find out about limitations, but also about unique opportunities and capabilities of the specific manufacturer that you plan to work with. And the same could be repeated for the partner universities. I'm not speaking for OSU alone. but the earlier you know what kind of challenges and what kind of tests you would need, the greater is probability that we will not treat you as a customer where you pay full price for this, but that we can apply together for external funding, having you as a partner, substantially reducing your costs. So that's my comment.
That's a great additional comment. Yeah, I mean, engaging with manufacturers, there's so much expertise and so much out there. That's definitely very helpful. And, you know, the more we can all work together, right? I mean, these meetups are great. We can share information, and the more we can connect and work together with the universities, it really is going to help leverage this, this material in the building industry. So.
And do it early. Have the manufacturer on at the table at the day one of your conceptual work.
Definitely. Any other great comments or questions?
We've got 2 minutes, so somebody's got to ask the perfect ending question here. No pressure.
What are the next projects that you have coming down the pipeline for CLT that you're excited about?
Oh man, what projects aren't we excited about? I mean, I know there's some, obviously the Adidas campus that's just about to complete construction that we're super excited about. I mean, anytime we can kind of open up a building, that is a great feeling from the whole team. From projects in the pipeline, I mean, everyone is so unique that we have, personally, I know I'm getting really excited about the Beaverton Central to see how that's going to, what that's going to turn into. Jack and Reid, do you want to talk to any that you kind of know and are looking into?
I don't know how much we can share on the projects that are currently in design, but just because of the development groups and their desire to keep those hush hush. But we're certainly in the process of designing more, and we only see more interest from developers and architects for using mass timber.
I'll take a slightly variation on the question. I'll say I think what I'm interested in looking at next is how to potentially the application of MPP in lateral force resisting systems. I think that's something that hasn't been explored enough. And like I was showing on that one slide, there's a stiffness benefit there that I think needs to be sussed out a bit. It's probably not all good news. I think some of the testing that's in its infancy at OSU is showing potentially slightly less deformation capacity in the nonlinear range for MPP. So maybe you get a benefit on the elastic side and a disbenefit on the inelastic side. But I think that's something that we will want to look at as an industry going forward.
Great, thank you. And Jack, don't worry, we won't tell anyone, any of your designers that, oh, just kidding.
Great, well, that's perfect timing. It's 5:30 on the dot. So I guess I would like to ask everybody to either unmute your mics and clap or do the little clap icon. Best speakers, thank you guys so much for taking the time.
It was our pleasure.
Yeah, awesome presentation. So,
It was a lot of fun.
Yeah. I will be posting the recording as long as that's okay with everybody at KPFF within the next couple days. And I'll include a link to basically the upcoming events as well. So keep your ears peeled. And yeah, thanks everybody.
Great. Thank
All
you.
right.
Have
Thanks.
a good evening.
Well done, KPFF.
Thank you.
Thank you.
Bye, everybody.
Bye.